action. Hello and welcome back to Calculus 1, the highlight of the semester, right? We are setting up for Calc 2 over here. I mentioned at one point that most of the problems in Calculus 2, integration part of Calculus 2, are going to be either algebraic or calculus manipulations to get the problem ready for U sub. Now, in chapter 3, you guys learned all types of differentiation techniques. And I singled out one of them as the most important. Not the most powerful, but the most important. Does anyone remember that one? No, that's the most powerful. What was the most important one? That is pretty much always present when you're doing derivatives. Chain rule, yes. Chain rule. So chain rule is the most frequent and the most used derivative of all of them, right? Sure, product, quotient, and all of these guys pop in, right? Basic ones, pretty much no, never, right? So the chain rule is the one that it's there most of the time. We also know that anti-derivatives undo derivatives. So it would be natural to learn a technique that will undo the chain rule. And that's what the U sub is. So what is the U sub? We should write that clearly at the beginning of the lecture. U sub is going to undo the chain rule. What does this mean? Well, if I had the derivative d dx of, let's say, sine 5x to be 5 cosine 5x, that needs to be now integral of 5 cosine 5x dx needs to give me sine 5x plus c. This is what we are trying to achieve. What is the method that we are going to use on obviously much spicier examples to convert to go back between integration derivatives this way? So let's start slow. I would like to integrate x plus 13 dx. You know the rules. Integral of x is x squared over 2, and integral of 13 is 13x. You put plus c, and you walk away. Done, right? The next one is, I said, all right, let me make it a bit spicier. So I square this. You say, not an issue. I'm just going to FOIL this, right? And I said, okay, fine, you win. So you go x squared plus 26x plus 169 dx. And then you integrate each one separately to get x cubed over 3 plus 26 times x squared over 2 plus 169x plus c. Then you cancel 26 and 2 to get your 13, and you win. You were able to complete that problem. And then I say, okay, fine. X plus 13 raised to the 79th power dx. Good luck foiling. Right? And this is where issues, right, become real. You're looking at this and you're saying, so I'm not going to FOIL this, right? So what should we do? And this is where the technique that we are learning kicks in. So basically what this technique says is, if I could just make this to be like one thing, you see what I did with it? Then I would have that one thing raised to the 79 power, and I know how to integrate x to the 79, right? So let me make this thing over here one thing, and then try to deal with the integral. So you say u equals x plus 13. Now, what are you effectively doing here? You are changing variables from x to u, right? It's called u substitution. You are substituting u's for x's. Okay. Remember that this piece over here was not there for decoration? Do you see that the variable for it is x? Well, now that you are changing this x over here, you better change this x as well. Or I call discrimination. Right? So, the way to do that is you will differentiate this. Someone's stuff is done in my field. And then I'm going to move this dx to the other side, and for this particular problem, du equals dx. Nice. Let's substitute. Well, integral is still integral. X plus 13 is u. I have the 79 power, and instead of dx, I write du. Yay! I got to change all of the x's into u's, and in the process get a very simple problem to do. What's the integral of u to 79? U to 80 divided by 80 plus c, right? You just integrate normally because you have a polynomial now. And you know that that's the x to the n plus 1 over n plus 1. It's just the standard stuff. How do you integrate x squared? You go x cubed over 3. How do you do that for x to the 20? Well, it's going to be 21 over 21, right? You go plus 1. So if you have 79, it's going to be 80 over 80. Good. But see, the question was posed in x's. Your answer over there is given in u's. So, what you must do? You must go back to x, right?
Change it back.
Change it back. So, we have 1 over 80, and then u is going to be x plus 13 raised to power 80 plus c. There is a sentence that you can quickly remember for this. I don't care about u, I care about the x. Which means, right, that you have the, right, you have to go back into x domain. Right? Okay. Let's see another example of this. So you have integral of 2x square root of x squared plus 9 dx. You are not allowed to do integrals part by part. No, 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 right? So what do? You say, well, what's the most complicated thing that I have over here? And I hope that you would all say, yeah, it's a square root, right? Because the other thing is 2x. It's easy. So let me try and make this thing under the square root u and see what happens. So u equals x squared plus 9. That's going to give me square root of u. And I can deal with square root of u, right? So you see, you reduce the order from squared to a linear, right? And then also you, too much, huh? So now what I'm going to do is I'm going to differentiate du dx. And what do I get on the other side? I get 2x. Then I move the dx to the other side. This is technically creating a differential, right? So I move the dx to the other side, and wow, look at this. Don't you agree that over here in this peanut, I have the du? You see 2x dx, they're all multiplied. 2 times x times dx. And I have exactly the same thing in here. So now I get to replace that. 2x dx gets replaced with du. So what do I have? I have integral of root u du. Just collapsed into it. So this part over here is u, and you get square root of u. What's around is 2x dx, and that's exactly what I have here. 2x dx is du. So I'm replacing whatever is underlined red with du. And so this is my blue one, and this is my red one. There you go. So this is u to the 1/2 du. You integrate that, you get u to the 3/2 divided by 3/2 because we are just adding 1 plus c. This is actually equal to 2/3 u to the 3/2 plus c. And now I don't care about u, I care about the x, which means is u becomes x squared plus 9 raised to the 3/2 plus c, and the problem is solved. This is the way these integrals work. You take something complicated and you collapse that to a single variable. Then you deal with the derivative and hope that the rest of the stuff is going to match it. And then you see 2x dx, 2x dx. So 2x dx is du. This mess is u, so square root of u times dx, which is du. And now I just need to solve this basic integral rather than this mess on top. That's what the u sub is all about. Let's do another example. It's the way these things go. Let's integrate two more basic things. Integral of e to the 3x dx. You know that the integral of e to the x is e to the x. So you know how to integrate when you have a single thing, single variable in exponent. Okay, so let's make it a single variable. U equals 3x. Well, what's my du now? Du is equal to 3 dx. Right, it's du over dx, and then you shift dx to the other side. Okay. I have integral. E to the x is become now e to the u. Because 3x is u. We are substituting. Again, u sub. Right, so you're substituting. And wow, now I have a dx, but it doesn't match. I don't have a 3. So you know what? I'm going to solve this that the dx is equal to du over 3. Plug that in, so dx is now du over 3. Do we all see this? Right? So I solve for dx because I have to plug in stuff for the exponent. I have to plug stuff for dx. That's always the case. So now I get to kick 1/3 in front of the integral, and I just have e to the u du, which is 1/3 e to the u plus c. Again, I don't care about u, I care about the x. So there we go. You know what I haven't done? I haven't checked any of these problems yet. So how about I check this one? Because I can. All I need to do is to take the derivative of 1/3 e to the 3x plus c and hope to get this. Otherwise, it's wrong. It's garbage. So we copy the constant 1/3. The derivative of e to the 3x is e to the 3x times the chain rule, which is 3. And derivative of constant plus c is 0. 1/3 cancels 3, and there it is. E to the 3x. Yeah, we're good, right? I'm just going to move this line underneath. Let's do another example and call it a day. The integral of, let's go with the cosine of 5x dx. Now, most of your advanced applications later on in engineering and so on will call for cosine omega t. T is the variable instead of x, and omega is angular velocity. You better be able to integrate and differentiate these things. Well, differentiation, you will clearly have the chain rule to kick omega out. So now we're learning u sub, so you can deal with these things with integration as well. Because, you know, other calcs are coming up, differential equations are coming up, so you need to be able to do that. Well, you know that the integral of cosine x is sine x. So you need to make this a single in order to integrate efficiently. So u equals 5x. Then du is 5 dx. And when you solve for dx, is du over 5. Time to plug everything in. Integral of cosine, instead of 5x I have u, and instead of dx I have du over 5. I will kick 1/5 in front of the integral and just deal with the cosine u du. What is the integral of cosine u? Anyone? Very good. Sine u plus c. Don't forget plus c, guys, for Thursday. And now we go back into our x variable. So 1 over 5 sine 5x plus c. And that's the answer. If you don't like it, you will try to prove it, right, or try to check it using the derivative. And you must get cosine 5x back when you differentiate your answer here. So the u sub method, these are the basic examples. We'll do more advanced stuff on Thursday after the exam. Part 2, right? There will be part 2 of this lecture. So what we do is we take the complicated integral, and by u substitution we make it very simple. We solve it, and then we bring the x variable back once the whole thing is done. So that's that. and we'll do more of these examples. We have more advanced examples to work with, and then we also have change of limits of integration, because these guys are also done on definite integrals. And your definite integral, a to b, those a and b are x values, and we need to change those to u's as well. So we will work on transforming limits, transforming function, and transforming dx. You will have to transform everything. So we'll extend our basic rules that we covered here and do more examples. I will see you all in 2 days.
Is there a stapler right under the desk?
No, there's a stapler in the math department.
Just wondering for the lab. Is it okay if it looks like this?
Yeah.
Yes.
Like, no.
I said anything is fine for the lab.
Well, do you just